Hello, everyone. Welcome back to Mathematical Statistics. I hope you had a good break. We are almost done. We are in the final stretch of the semester, and review problems for the final will be coming out next Wednesday and solutions by Thursday at the latest. And then after that, I'll give you some info about upcoming review sessions, but we still have more work to do. So let's get back to hypothesis testing. In the beginning of the course, we talked about hypothesis testing and mostly kind of guessed at what statistic we should use and then kind of reasoned the form of the test. Should I reject if this is large or this is small? But now it's all being automated for us. So that's a really great thing. I mean, to have a method in place. Not only do we have a method in place, but we are defining what are known as best and most powerful tests. And this is like the UMVU in estimation, but in hypothesis testing. So let me remind you, let me get my screen going here. Our parameter space is going to be in general some capital theta, and then we're going to have some capital theta naught be some subset of the parameter space. And our hypothesis, our null hypothesis, is going to be that theta is in this subset of the parameter space theta naught versus theta is in the rest of the parameter space, which is the complement of theta naught with respect to the original theta space. So again, if you had like a lambda and your null hypothesis was that lambda is greater than 1, your alternative would be the complement, but in the space. And if the space, if lambda is, say, a rate parameter or an exponential or something else, that's greater than 0. So the alternate hypothesis is going to be a complement with respect to this space. And we probably won't even bother writing this, but you do have to keep that in mind when you're doing the problems. So we have started out by looking at simple versus simple hypotheses. We're looking at the null hypothesis that theta equals theta naught versus the alternative that theta equals theta 1. You'll recall simple hypotheses are not completely defined by having equal signs, but a hypothesis is simple if, when you know it's true, you have completely determined the distribution that your data has come from. So if there's only one parameter and theta is one-dimensional, both of these hypotheses are simple because when the null hypothesis is true, I know the data has parameter theta naught. And the alternate hypothesis is also simple, but if there was a second parameter that was unknown, then just having these equal signs does not mean we have simple hypotheses. Okay, so we are talking about simple versus simple right now. And we also started talking about critical or equivalently rejection regions. We're using like a capital C for critical region. I guess you could use an R for a rejection region. And this is a set that if your data falls into, you're going to reject the null hypothesis. So our data, we're calling capital X. This is capital X1 through capital Xn. And I made it look like a row vector. It doesn't matter. I'm not doing actually any matrix operations here. So you might be in data more used to seeing X as a column vector, and that's fine too. But right now, the vector X is just containing all the X's. And so we are going to reject the null hypothesis in favor of the alternative if the data X is in this critical region. And the critical region has a certain size that we call alpha. Alpha is our level of significance. So alpha is the probability you reject the null hypothesis when you shouldn't because it's true when theta is theta naught. And now this is that the vector X is in C because C is your rejection region. And this right here is why I sometimes, often, all the time, call alpha the size of a test. In a more data-oriented course, it's usually called a level of significance, and it's absolutely fine if you call it that as well. But in more advanced stuff in probability, this function, this P, is measuring a certain set. It's it's like it's a function that you're putting a set into and you're measuring it, whatever that means. We're not doing measure theory in this course, but this is saying the measure of it or the size of it is alpha. So that's where the terminology size comes from. Okay. What else do we need to know before we can get going here? Oh, yeah. So suppose that C1 and C2 both have size alpha, and we are still talking about the simple versus simple hypotheses. You just be really clear about that. Then the probability you reject using the first test, that's what this is saying. Your data is in the first rejection region when the null hypothesis is true is alpha because C1 has size alpha. But this is also the probability you reject or are in the second critical region, so reject under the second test. And if they both have size or level of significance alpha, then this equation has to hold. But they can differ then when the alternative hypothesis is true. So C1 is said to be better than C2 if. So when the null hypothesis is true, we look at these probabilities and they have to be the same. But if you look at these probabilities, when the alternate hypothesis is true, so I'm going to put a theta 1 in there, the probability you reject the null hypothesis using the first test, when the alternate hypothesis is true, you definitely want to reject the null hypothesis when the alternate hypothesis is true. So you want this probability to be large. And we say that C1 is a better test than C2 if this probability is larger than the probability you reject the null hypothesis using the second test when you should be rejecting because the alternate hypothesis is true. Rejecting, the probability of rejecting is how we define a power function. And so this line could be written as gamma, the probability you reject, and then there's going to be two tests. So I could put a sub 1 or a sub C sub 1 and evaluate it at theta 1. This needs to be greater than or equal to gamma C2 at theta 1 in order for C1 to be better than C2. So we say that C1 has, more quotes in my quotes, higher power than C2 when the alternate hypothesis is true. Our better test is also a test with higher power. And now I'm going to remind you of how to define the best test, which is the test with highest power or the most powerful test. So C star is the best or most powerful test. And I'm not going to keep rewriting the simple versus simple hypotheses, but this definition is in the simple versus simple case. If for any other test C of size or level of significance alpha, we have the power function, the probability we reject under the test with C star. Sorry, I do mean that to be a lower subscript only because I want to start taking complements here. So there's going to be other superscripts. When the alternative is true, is greater than or equal to the power function under the test C when the alternative is true for any other C. That's what makes it best, not just better than a certain C1, but not just better than a certain C, but better than all tests, all critical region C. So we figured out last time how to come up with such a test, and we use the Neyman-Pearson Lemma, which we applied last time, and we were just getting started on proving it, so that's where I want to pick this up. So if you have the simple versus simple hypotheses that look like theta equals theta naught versus theta equals theta 1, and you look at the likelihood ratio that I was calling lambda, which is a Greek L for likelihood of X, either lowercase or uppercase, theta naught, theta 1. This is defined to be the joint PDF when the parameter is theta naught over the joint PDF when the parameter is theta 1. The best test is to reject the null hypothesis in favor of the alternative when this is small. Because if you think discrete random variables, then those joint PDFs are representing probabilities. The numerator is the probability your capital X1 through capital Xn is equal to lowercase x1 through lowercase xn when the null hypothesis is true, and the denominator is the same thing when the alternate hypothesis is true. So if you have a higher probability of seeing that data when the alternate hypothesis is true, that will make the denominator of this fraction larger and the whole thing smaller, and that is lending support to the alternate hypothesis being true. So we want to reject when this likelihood ratio is small, being strictly less than, or Neyman-Pearson usually has it as a less than or equal to. It's not important for our continuous distributions, but it could be important. Some constant. Now, usually we call our cutoff C, but because there's all these other C's floating around here, I started to call the constant K, where K is determined in order to give a size or level alpha test. So where's the C star? I didn't explicitly write it there, but the C star, the best critical region, is all of the X's for which this likelihood ratio is less than or equal to K, where K is chosen to give the size alpha test. And then the final rejection rule is going to be to reject the null hypothesis in favor of the alternative if the data, the capital X's, are in C star. So that was our Neyman-Pearson lemma. And again, that is what you go to find a best or most powerful test when you have simple versus simple hypotheses. We did at least one example last time. I will do more this time, but we were to the point where we wanted to prove this. And one more thing before that was notation. So if you take like a set A as a subset of the n-dimensional reals, if you want to find the probability that the vector of x's, capital, so probability makes sense, is in A when the parameter is theta, or maybe theta naught, or maybe theta 1, this is going to be an n-dimensional integral or sum, if things are discrete, of the joint PDF when the parameter is theta, and we're going to integrate dx1 through dxn, and these limits of integration will describe the region or the set A. And our notation for this, I was going to say new, but we've used this once or twice before. So just as a reminder, we're writing this as a single integral over an n-dimensional set of a PDF and then a dx with a vector over the x. This is going to be really useful for us. It has been in the past, and it will be for this proof as well. So let's prove the Neyman-Pearson lemma. Okay, so I'm going to start out by letting C sub star be the critical region described by the Neyman-Pearson lemma. We're going to include points in it if when you evaluate the likelihood ratio, the ratio is less than or equal to K, where K has been determined to give a size alpha test. Let me write it for the record here. I'm going to let capital X as a vector be x1 through xn. Again, I'm not actually doing matrix operations, so I don't really care that this is a row vector. If you want it to be a column vector, that's okay too. And now I'm going to say, suppose that you have a set A that is a subset of C star. Now, I'm not saying that A is a rejection region or has size alpha or anything like this. It's just a subset, and I just want to characterize certain probabilities of being in certain subsets of C star. So if A is a subset of C star, then we have that the ratio f of x theta naught over f of x and theta 1 is less than or equal to k for all vectors x in A, because x is contained in C star, and all the x's in C star satisfy this inequality when you plug them into the likelihood ratio. That means that this is less than or equal to this times this. PDFs are not negative, so I wouldn't be flipping anything by multiplying that denominator to the right-hand side. And so we can say the probability that the random vector of capital X's is in A when the null hypothesis is true. The definition here in our new notation is the integral over A of f of the vector of x and theta naught dx. And if x is in A, we have this inequality. So that means this whole thing is less than or equal to k times the integral over A of f of x and theta 1 dx. But integrating the joint PDF over this region, this gives us k times the probability that x is in A when the parameter is theta 1. Bottom line, if A is a subset of what we're calling the best critical region, and we're out to show that it is, then the probability we're in A when the null hypothesis is true is less than or equal to k times the probability we're in A when the alternate hypothesis is true. So similarly, I'm just going to write, on the other hand, if A is not contained in C star, but contained in the complement of C star, then we get that this likelihood ratio, by definition, if X is in A, then X is not in C star. And that means that for those X's, this ratio is greater than K for all X in A. And so if you do the same sort of thing we just did, writing out probabilities, you'll get so this implies the probability that the vector of x's is in A when the null hypothesis is true. This is greater than k times the probability that x is in A when the alternate hypothesis is true, in the case where A is in the complement of C star. So I just wanted to establish these two facts given by these green circles, and then the other case. And I won't say that again because I've said it a few times and I'm going to scroll back. So I'm just going to repeat myself maybe a little too much. But let's go back to a test of size alpha. So I've got the C star defined by Neyman-Pearson, and I want to show that it's best. So I'm going to let C be any other test of size or level of significance alpha for the given hypotheses. This is probably not a subset of C star or a subset of its complement, but actually before I do that, the goal, well, before I do that, if it's another test of size alpha, then the probability that the random vector x is in C when the null hypothesis is true is alpha. And the goal is to show that the power function for the C star test when the alternate hypothesis is true, so this is the probability you reject when the vector x is in C star, when you should reject because the alternate hypothesis is true. We want this to be large. We want this to be greater than the same thing using any other test of size alpha. So this is what we need to show right here. Okay, so as I was saying, C is probably not a subset of C star or the complement, but check this out. We could write C star as the part of C star that intersects with C, union the part of C star that intersects with C complement. Why I'm writing so large, but these are disjoint. And so if you wanted to look at the power function, remember, where are you? This is what we want to show. So right now I'm going to attempt to write down the power function on the left-hand side with any argument theta. I can plug in theta 1 if I want, but I'm not going to do that yet. So the power function for the C star test, this is the probability that X is in that C star critical region when the parameter is theta. And this is made up of this unioned with this. So the probability you're in a union of disjoint sets, you can get, because they're disjoint, you can get this probability by summing the two individual probabilities. So this is the probability that X is an element of C sub star intersects C when the parameter is theta, plus the probability that X is in C sub star intersects C complement when the parameter is theta. And let's do an on the other hand. So on the other hand, we could write that C is the part of C that intersects with C star, unioned with the disjoint piece, the part of C that intersects with C star complement. I'm just going to take a moment to rewrite this in the other direction. I mean, intersecting two sets, it doesn't matter what direction you intersect them in. So most of you are going to think this is silly, but just in case, I want it to look like the set above. And I'm just going to leave this one, or you can change those as well. But the power function for the C set is now and these are disjoint sets. So this is the probability that X is in C when the parameter is theta. And this can be broken up into the probability that X is in C star intersects C when the parameter is theta, plus the disjoint event probability that X is in C intersected with C star complement when the parameter is theta. Okay. Again, look at the green box. I'm trying to show that the power function for the C star test when you plug in theta 1 is greater than or equal to the power function for the C test when you plug in theta 1. So I'm going to look at the difference. I am going to look at the power function for the C star test at, let me not plug in theta 1 just yet. I'm going to look at a generic theta minus the power function for the C test at a generic theta. So I've got this line minus this line, and the first terms are just going to cancel. And I'm left with the probability that the vector X is in C star intersects C complement when the parameter is theta minus this probability that the data is in C intersects C star complement when the parameter is theta. So maybe I should have done theta 1s, but you know what? I have a reason for holding off. In the next line, I'm going to plug in theta 1s. So let's put in theta 1 for both of these thetas. This is a set, and it is, because it's C star intersected with the complement of C, this is contained in C star. This is like the A set I was talking about earlier. And so I know that, so let me back up to that. When A is contained in C star, I know that this probability is less than or equal to K times this other probability. Now, the probability I've written down with the final line on my slides actually is this one. And so I'm going to put that K to the other side. I'm going to say that this entire term is greater than or equal to 1 over k times the probability that x is in C star intersects C complement when the parameter is theta 1. That's me using that property we had above. If A is a subset of C star, then. And then over here, this set is in C star complement. So going back and using the property that if A is in C star complement, let me do that. Okay, so in the case where A is in C star complement, we have this. And right now I'm looking at an expression like this, but A is defined to be something really specific. So this is less than 1 over k times this. So this is less than 1 over k times the probability that x is in C intersects C star complement when the parameter is theta naught. The entire line is greater than or equal to 1 over k, this first probability, and then I'm subtracting something that is smaller than this. So this is the largest thing I could subtract, making overall the right-hand side the smallest, which is why I get this inequality by having minus px in C intersects C star complement theta naught. Hopefully that makes sense. As usual, the hardest part of hypothesis testing, I think, is just all the notation. Because what we're doing here is, it looks crazy, but it's not really bad at all. It's just so much notation. But this difference, and both of these, this should be a theta naught. This difference is this again, but with theta naughts plugged in here and here, and therefore here and here. So this is 1 over k, the power function, with C star theta naught minus the power function with C and theta naught. Right, so I am right now using the line at the very top of the screen. I used it before and I'm using it again. But now I'm plugging in the theta naughts. And both of these, I mean, this is the probability, right? That X is in C star. So you're rejecting, my star went to the wrong place, when the null hypothesis is true. And this is going to be alpha. And because this is a similar statement, but with C instead of C star, and C has size alpha, that's also alpha. This is 1 over k, alpha minus alpha, and is 0. This is greater than or equal to 0. And we are done. We have shown that the power function for the C star test, when the alternative hypothesis is true, this is greater than or equal to the power function for the C test when the alternate is true. And this holds for any test, C with size alpha, any test. And this means that C star is the best test of size alpha for the given simple versus simple hypotheses. So we are done proving the Neyman-Pearson lemma, which is proof by notation. It's really, if that made sense, great. If not, that's also okay. I'm not going to test you on this, but if you want to understand it, just keep looking at it until the symbols gel for you, because it's not that difficult, but there is a lot of notation going on here. Okay. So we proved that the Neyman-Pearson gives us the best test, and that is for a simple versus simple hypothesis, and the best test is also known as the most powerful test. I want to move on to making the alternative hypothesis composite, But I'm going to do that sort of mid-example. So let's look at an example to get another Neyman-Pearson in. Suppose that x1 through xn are IID from the beta distribution with parameter theta and 1. Then this means that the PDF, it has that beta function in front, and then is x to the theta minus 1, and then 1 minus x to the 1 minus 1, which goes away, and an indicator saying that x is between 0 and 1. And if you look at that and figure out the constant you need for this to integrate to 1, you'll see that this is theta, even if you don't remember what the beta function is. So part 1, maybe I'll call it A so it'll look more like subparts here. Let's find the best, or equivalently, most powerful test of size or level of significance alpha for testing the null hypothesis that theta is some theta naught versus the alternative that theta is some theta 1. Theta naught and theta 1, as usual, are stand-ins for numbers. Like, don't get thrown if on the final I actually give you numbers and say theta equals 1 versus theta equals 3. There'll be two numbers you can compare, and one is clearly larger than the other. But here it's not so clear, so I have to tell you this part. So for theta 1 greater than theta naught, I want to find the best or most powerful test for this. And heads up, we're not going to be able to get an exact critical value. You could integrate numerically and find an approximate numerical critical value, but we like to always sort of return to the chi-squared distribution because it's so central to statistics. And I have a theorem coming up where you're going to see the chi-squared distribution in a limit in a kind of general setting. So right now it's just an exercise. Let's do it. The PDF is sitting right there, so I am ready to write down the joint PDF. Because these are IID, they get to multiply as I goes from 1 to n, the individual PDFs. And if you plug them in and multiply, you get theta to the n. You get a product of the xi's each raised to the theta minus 1. We know we can pull that product in and say we have a product completely raised to the theta minus 1 and a product as I goes from 1 to n of indicators. I'm going to form the likelihood ratio. This is a function of the data, theta naught and theta 1. This is the joint PDF with theta naught plugged in over the joint PDF with theta 1 plugged in. So I'm going to write this entire thing with theta naught in the numerator, theta 1 in the denominator, and I'm going to go ahead and start simplifying it right now. I'm going to end up with theta naught over theta 1 to the n, the product as I goes from 1 to n of the xi raised to the theta naught minus 1 minus the quantity theta 1 minus 1. So the ones will cancel, and we'll have theta naught minus theta 1. And those indicators do not depend on the theta, which is the only thing changing in the numerator and the denominator. So those are going to completely cancel. And the form of the test is going to be, we want to reject the null hypothesis in favor of the alternative if this theta naught over theta 1 to the n, the product as I goes from 1 to n of the xi raised to the theta naught minus theta 1 is less than or equal to k for some k to be determined. On the final, if I say, just give me the form of the test, then I'll be specific. I'll say the form of the test. This means you do not have to actually continue and find the k. But this one, we're going for it. We're going for it. So I think the easiest thing to do is to try to isolate the x's. The first thing I'm going to do is I'm going to take this and divide it to the other side. And because these are A out of the A and B parameters for the beta distribution, these are positive numbers. So I know I'm not dividing by anything negative. And when I divide that thing I just circled to the other side, I will maintain the inequality in that direction, and I'll get a new constant that I'm going to call K1, which is the old constant divided by the thing in the yellow circle. I don't really care to keep track of the constants. You can if you want. I'll talk about that again at the end. So how are we going to deal with this exponent? We could try to take the 1 over theta naught minus theta 1 root on both sides, but knowing what's coming ahead, like us having to find that k, I would like to not be dealing with a product of random variables, but a sum. So I want to take the log on both sides. The log is a nice monotone function. On the left side, we get to bring down that exponent, theta naught minus theta 1. The log of the product is the sum of the logs. And if you didn't write that, then you didn't write that, but you're going to end up doing it later when you realize that sums are much easier to work with. Finally, I want to divide that coefficient over, and in this problem, we had that theta 1 was greater than theta naught, and that makes this negative. So when we divide, we will get this flipped, and there'll be a new constant here, K3, which is K2 divided by theta naught minus theta 1. Okay, so the form of the best test for theta equals theta naught versus theta equals theta 1, where theta 1 is greater than theta naught, and the data are IID from the beta distribution with parameters theta and 1, is to reject the null hypothesis in favor of the alternative. I'm not going to try to catch you on that on homework or exams, but we have simplified the parameter space here. The A parameter for the beta AB distribution, which is our theta here, can be any positive real number, but we're restricting to 2 hypotheses. So that's our entire world right now. And so it is important to say, I'm not just rejecting this, but I'm rejecting it specifically in favor of this other hypothesis. So here I want to make sure everything is nice and capital. The sum as I goes from 1 to n of the log of the capital Xi is greater than or equal to K3. Or just call it K at this point, but know that it's not the original K. And I don't know if you like that, having the log in there. Maybe you want to do some E stuff and redo it to try to get down to the product of the X's again, but I don't think that's worthwhile. If you do, you do. But in the end, I want to give a recipe for someone to do the test. And my recipe is going to have this form. I like it. Okay, so the next step is to find K3. And this is where alpha comes in. So alpha is the probability you reject the null hypothesis when you should not, because it's true, because the parameter is theta naught. And rejection here means that the sum as I goes from 1 to n of the log of the xi is greater than or equal to K3 when the null hypothesis is true. So now I need to make this neater is what I need to do. But we need to deal with this statistic. This is back to the first couple of weeks of the course, starting with xi having a beta distribution with parameters theta and 1. And actually, for this probability statement, theta is going to be theta naught. If you let yi be the log of xi and let this be g of xi and do the g inverse formula, you're going to see that the PDF for y is theta e to the theta y on minus infinity to 0, which is looking exponential, but a little bit messed up. So instead, if I let yi be the negative log of xi, we can go through the same procedure and we'll get that the y's are IID exponential with rate theta only after I've defined it properly with a negative. Let me go back to, sorry about this, it's not so easy when you're taking notes, but I'm going to copy and paste this here. I am going to put negative in here. And actually, let me just multiply both sides by a negative. So this is the probability that after multiplying both sides by a negative, well, here, I'll do it. Negative I goes from 1 to n of the log of the xi greater than or, oops, sorry. This is flipping, of course. And I'm going to put a new constant here, k4, where k4 is the negative of k3. So you might be wondering why I wrote that down, because before I just kept changing the constant. It's k4, it's k5. I'm giving it new names. Why am I keeping track at this point? I don't have to. It just depends on the form of the test, how you want to give the test at the end. I am going to stick with this fine paragraph here. I'm going to give this as my test, which means I need to return the k3. If you want to say, look at the sum of the negatives of the logs and reject if it is less than or equal to k4, where you instead give k4, that's fine. Again, you could just say it's a new constant and kind of drop all the other stuff. You have to kind of pick a part where you're finally going to state the form of your test. If you want, you could keep track of k3 and how it relates to k2 and how it relates to k1 and how it relates to k, and then say your test is going to have this form where you give the k, and that's, I guess, okay. But I'm going to stick with this one in this big circle blob thing here. So I do care to find k3 and not k4. This, not that you need to write this line, but this is the sum as I goes from 1 to n of the negative of the log of the xi. So right there you see the exponentials in the parentheses. And the parameter is not just a generic theta here, but it is theta naught. And if it's theta naught, then this is exponential with rate theta naught, which makes this entire thing, because they're IID, it has a gamma distribution with parameters n and theta naught when the null hypothesis is true. We're going for the chi-squared critical value. So you know we want to get rid of this theta naught, and we want to get a 1/2 in there. And given the way we parameterize the gamma distribution, anything we multiply by ends up under that second parameter. So I am going to continue here, and I am going to multiply both sides by 2 theta naught. That won't flip anything. And now, this has a 2n 1/2 distribution, which is a gamma distribution with parameters n and 1/2. And this is 2n over 2 1/2. And this is a chi-squared 2n distribution. So I'm going to call this whole random variable, say w, where w has a chi-squared 2n distribution. And I didn't write this. It wouldn't be wrong if I wrote it, but it's not necessary anymore because the distribution of w is completely known to us, regardless of what value theta naught takes on. So the information isn't really relevant at this point. And this whole thing way up here was alpha. So if I look at a chi-squared 2n distribution, I want to be below some number with probability alpha. That means we're above it with probability 1 minus alpha. And for our critical value notation for this class, we call this number chi-squared sub 1 minus alpha, comma 2n. You can call it whatever you want, as long as you're clear, drawing a picture is clear, or you explain what your notation means on the homework or an exam. But in our notation, 2 theta naught k4 is equal to chi-squared sub 1 minus alpha, comma 2n. This means that K4 is chi squared 1 minus alpha comma 2n over 2 theta naught. And K4 was K3. So, I'm sorry, it was the negative. So K3 is the negative of this chi squared critical value over 2 theta naught. So the final test, I'm going to go back and grab that big bubble statement. We are going to, let me just grab a part of it here. I'm going to reject the null hypothesis. Okay, so we're going to change out the K3 to be the negative of chi squared 1 minus alpha, this critical value for the chi squared 2n distribution that cuts off area alpha to the left and 1 minus alpha to the right over 2 theta naught. And this direction stuff should make sense because the x's had a beta distribution. So they live between 0 and 1. The log of numbers between 0 and 1 are between minus infinity and 0. So both sides are negative here. If you want to take the negative on both sides, do that if it bothers you. But that's it. This is the best test of size alpha for this beta distribution for testing the null hypothesis that theta equals theta naught versus the alternative that theta equals theta 1, where theta 1 is given and known to be greater than theta naught. So all of that was part A to this problem. We had this beta setup and we found a best test. Part B, I want to ask you a different question where I'm actually defining a big thing here in the question. I want us to find the uniformly, this is what I'm defining actually, most powerful, otherwise known as the UMP test of size alpha for, so I'm sticking with the same setup, the betas, but I want to now kick us up to a simple null hypothesis versus a composite alternative hypothesis. So I'm going to say theta equals theta naught versus theta is something greater than theta naught. We have never done a uniformly most powerful test. I'm slipping the definition into this problem. This is best or most powerful uniformly, and you'll recall uniformly in math means for all. The UMP test, uniformly most powerful test, is best or most powerful for all or for every simple hypothesis included in the alternate hypothesis, which has a bunch of hypotheses. Theta is greater than theta naught means theta could be a whole lot of things. We know what best or most powerful is when we have simple versus simple. When we have simple versus composite, we could talk about a test that's uniformly best. So we want our test to have size alpha. So we want our data to be in our critical region and call it C star if you want to. But when the null hypothesis is true, we want this to be alpha. And when the alternate is true, I don't know what theta is. I don't have a particular one here, but for each and every theta 1 in this set, I want this test to be best and not to depend on that choice of theta 1. I want it to be best or most powerful for all simple hypotheses contained in the alternate hypothesis. The way to find one, which is why I just kind of snuck this big idea in here, in just a part B of an example, is the method is going to be, so step one is going to be to first consider the simple versus simple. So maybe this wasn't a part B, but you were given this beta stuff and you wanted to find a uniformly most powerful test for the circled hypotheses. The first thing I would do would be to kind of simplify it to a simple versus simple theta equals some theta 1, where this is one hypothesis picked out of all of these hypotheses. So where theta 1 is some number greater than theta naught. This is now part A. So you would, assuming you didn't already do it, you would use the Neyman-Pearson Lemma to find the best or most powerful test for this simple versus simple scenario. And we just did it. Let me try again with the copy and paste. So dot, 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 right? Usually at this point, you're then going to have to do it, but we already did it in part A. Now look at this test. There's no theta 1 in there. You could have stopped with any of the other constants, K, K1, K2, K3, and maybe had, but our ultimate test here, the recipe we're giving to the people with the data, is you take your data, take the log of everything and sum them up and reject the null hypothesis if that sum is greater than this number, and nothing about this rule involves theta 1. So this doesn't explicitly depend on theta 1, but it kind of has a hidden dependence. It did depend on the fact that theta 1 was greater than theta naught, because when we were deriving this, at some point we divided both sides of an inequality by theta naught minus theta 1. And theta 1 being larger made this thing negative, and it made an inequality flip. So it did affect this. So this test doesn't explicitly depend on theta 1 and the fact that there's no theta 1 in this circle. But the fact that theta 1 was larger than theta naught is kind of in there. But this will work for any theta 1 greater than theta naught, and that's what we're after here. So step 2 of this method is to note that, you know what, I just wrote it, but this test does not depend on the theta 1 chosen, although it does depend on theta 1 being greater than theta naught. Other than that, it works for all of those theta 1s we could have chosen when we took our simple versus composite hypothesis and considered a simple versus simple for many different given theta 1s. This test that's in the circle now is the best or most powerful test that works for all theta 1 in that region. And so to finish this off, it is uniformly best or most powerful for the hypothesis that theta equals theta naught versus the alternative that theta is greater than theta naught, because there was no actual theta 1 in this part of the problem. So I had a big definition in that example. The uniformly most powerful or uniformly best test is we're getting to composite versus composite. Right now we have simple versus composite, and you pick every single hypothesis in that composite and consider simple versus simple. And if your test is best or most powerful for everyone, you don't have to change the test depending on the theta 1, then it is uniformly most powerful. Okay, I have just enough time to throw in a part C. And this is going to be find if it exists, which is a big giveaway because when do I ever say that? A UMP test. So this is still part C of my beta example, so I don't want to take the time to rewrite the setup. Or the new set of hypotheses that theta is theta naught versus the alternative that theta does not equal theta naught. To start this, you would, like step 1, consider the simple versus simple So you would fix the alternate hypothesis to be like theta equals theta 1 for some theta 1 not equal to theta naught. And you would form the test. You would do exactly what we did all the way through. And you would end up with rejecting the null hypothesis if the sum of the log of the xi is greater than or equal to negative I squared sub 1 minus alpha comma 2n over 2 theta naught if this theta 1 that you choose is greater than theta naught. But that part where we divided by this and it flipped an inequality, if your theta 1 is smaller than theta naught, then that thing I just circled there is positive and you would not flip the inequality. So it would be to reject the null hypothesis if the sum of the log of the xi is less than or equal to something. It's going to be kind of like this, but a little bit different. The 1 minus alpha will end up being the alpha. You have to draw the critical region. I'm not bothering because as of now, I can already tell you that the best test for certain theta 1s from all of these possible thetas, the best test is going to be reject if the sum of the logs is greater than or equal to something. And for other theta 1s, the best test is going to be to reject if the sum of the logs is less than or equal to something. And these happen to not even be the same thing, but I don't care if they are because the tests are different. One says reject if it's too large, and one says reject if it's too small. There is no one best test that works for every theta 1 we could choose out of this set of composite hypotheses. So I am almost out of time. Let me say that this is the best or most powerful test if theta 1 is chosen to be greater than theta naught. And then this one is the best or most powerful test if theta 1 is chosen to be less than theta naught. So there is no best or most powerful test of size alpha for the null hypothesis that theta equals theta naught versus the alternate where theta is not equal to theta naught. UMP tests do not always exist. This is often the case for a two-sided alternative like it was here, but not always. We saw that at some point we divided by this, and it caused an inequality to flip. Don't write this down, I'm changing the problem. But if the PDF were such that we had like this squared, when we divided that, when we were taking our likelihood ratio less than or equal to k and saying less than or equal to k1, less than or equal to k2, flip greater than or equal to k3, if we had to divide by something like this, it's always positive, even if theta 1 is less than theta naught. And so we would get one type of test, one form of a test, and we would find the K4 or whatever it is. And so it is possible for a so-called two-tailed test like this to have, or two-tailed hypotheses to have a UMP test. But it is often the case where you'll get something with some kind of form and something with a different form, depending on exactly what alternative hypothesis you're choosing from this. So there is no best or most powerful test. No UMP exists. Again, that happens a lot with a not equal sign in hypothesis testing, but not always. So a little rush at the end. I hope that makes sense. When we come back, we're going to make that null hypothesis also composite and talk about UMP tests and when they might exist. And UMP tests are difficult. Remember how I said in estimation, the UMVU is the greatest estimator in all the land. It's, the best estimator you could possibly have. No one can do any better, but they can be difficult to find. They might not even exist. And I said the workhorse estimator in statistical inference is maximum likelihood estimation. This UMP test is like the UMVU. It is great. It is the best, but it might not exist, or it might exist but be too difficult to find. There's another form of generalized hypothesis testing that is kind of like the MLE is to estimation. And this is known as a generalized likelihood ratio test. We're going to talk about that next time on mathematical statistics.